Hello, welcome back. So in the last video, we talked about one particular form of effects or terms that show up in the equations when we have a term multiplied by the velocity. And we saw under certain conditions, those are the dissipative forces showing up. So let me actually write that down. So we saw dissipative forces where Q's on Qi, they were coming from these terms were coming from dissipative forces such as Q's. That, by the way, I made a mistake about this sign. So I made two mistakes. In the last video, this sign was positive and I made the sign of F to be negative. These two have to be flipped. Q is negative, F is positive. Anyways, so what am I doing? Using J from 1 to N, Cij Q dot J. So these kind of terms came from dissipative forces, and if they were dissipative, these Cijs were kind of positive. I'll mention in more detail what that means, but they are roughly in the idea of being positive. Gyroscopic terms, gyroscopic effects or forces, they take a very similar form. J from 1 to N, Gij Q dot J. But in this case, these coefficients Gij are, again, this is the weirdest I can talk, but they are kind of orthogonal. What that means will be evident later. But long story short, Gij should be opposite of Gji. So that's what we mean. And if the terms have these properties, what we're dealing with is a gyroscopic effect. So let's study this in a bit more detail. Most importantly, knowing where these effects come from. Dissipative forces came from some form of damping element that eats into the energy of the system. Gyroscopic forces come from a completely different origin. So their origin is actually in the inertial effects within the system, regardless of any external forces. So to see where they come from, they come in the equations, they show up they originate from kinetic energy. So if you recall in the kinetic energy formulation in the configuration space, we had a few terms. So there was this one, sum of I from 1 to N, sum of J from 1 to N, Mij, which could be functions of positions, Q dot I, Q dot J. So this was the kind of the familiar term we had in 1/2 m velocity squared in that space. Plus, we had another set of terms. Am I using J? Yes. J from 1 to N. Sorry, they're too close to each other. Some functions AI, again, possibly function of positions and time, dot Q dot I. So this is a quadratic term. I have Q squared. This is multiplied just by Q. And we had another term, let's call it T0. And this is, let's call it T1. This is where these gyroscopic effects originate. To see how they come into effect, so remember I have this Lagrangian, which is potential energy minus kinetic energy minus potential energy, and I take the derivative with respect to q dot and then the time and all of that. So I can do all of that, but let's only focus on this particular term in the kinetic energy. So what I'm going to build is this d over dt of partial t1 partial qi minus partial t1 partial q. This is q dot. So I want to construct this, see what happens. So let me rewrite this. T1 is sum j from 1 to n ai q dot I. No, q dot j. What are my indices? Oh, what did I have here? This here, or let's call this I from 1 to n. Yes, this is I. Okay, let me write this up. Sum of I from 1 to n. Okay, this is what it is. So first one is I have to take the derivative with respect to q dot. So partial t1 partial q dot I is going to be just this one. This is also I. So I only have one q dot I among all of the possible iterations of I, and this AI is the only one that comes out of it. And then I want d over dt of this AI. And remember, this AI is a function of q and t. And this one I can write it as sum over, now this one I'm using j, 1 to n, a, let's do partial a, ai partial qj, q dot j, plus possibly partial a I partial t. So that is the first set of terms. The next one is partial. I'm looking for partial t1 partial q1 or qi, sorry. So I have, what I can do is just change the index for this, change it to j because that makes things easier, and then take the derivative with respect to qi. So in that case, it's only going to be q dot j is just something on its own. If I do that, the only thing remains is ai, and what I need is partial derivative of that ai with respect. It's going to be, let me write it down. So to do this, let me write it this way. T1 is, I'm just going to change j equals 1 to n, aj q dot j. All I did was change the letter from I to j. And now I want T1 to QI, that is easier. So it's going to be any of these AJs, the partial derivative with respect to QI. So it's sigma J from 1 to N, partial AJ, partial QI, and I'm not touching this Q dot J. Now I subtract these two together. So this little trick actually helped me because now I have two summations over j, and I have this q dot j common, so I can factor that out. So then this thing that I'm trying to find, d over dt of partial t1 partial q dot I minus partial t1 partial qi, it's going to be sum of j from 1 to n, that thing, partial ai partial qj minus this thing, partial aj partial qi times q dot j plus partial ai partial q, I'm sorry, partial t. And now you can see where that kind of term shows up. This is actually my gij, which is multiplied by q dot j to give me the same form as I had up there here. And notice that this gij is the opposite of gji, and it fits the requirements for our gyroscopic effect. So this is where this term comes from, and you can contrast it with the other dissipative force, completely different origins and completely different properties. Let me add a little bit more. So when we're talking about this kinetic energy, remember what this AI was. AI is, if we write it in terms of the Cartesian coordinates of our particle, so k from 1 to 3n, partial xk, partial, oh, we're missing an mk, partial xk, partial qi, partial xk, partial t. So I want to draw your attention to two things. One is we're talking about some kind of inertial effect. So this, because of inclusion of this inertia in the equations, so this effect that we're dealing with is somehow an inertial effect. The other one, still keep uses, is this term, meaning that if, remember where these terms came from, they came from the conditions or situations when we have these external effects that would change the system, produces changes within the system outside the dynamics itself. So these externally induced movements are one thing that has to be present for the system to show, for our system to show these gyroscopic effects. So must have some change with time. And this one tells us these gyro effects are some inertia effects. And the last thing I want to mention here is that we sometimes hear that the name gyroscopic force, but it should be noted that these quote-unquote forces are not really a force, they are an inertial effect that are present within the system. But I can take terms like this, so these are on the left-hand side of the equation when we write the Lagrange's equation. I can take it to the right-hand side and treat it as a force, and that is what we are doing here up there, defining these G's. These G's kind of have the flavor of a force. The unit is Newton, so they have the right unit to be of a force. And that's why we, similar to the condition that we had with the Lambert's principle, that we treated accelerations as some kind of inertial forces. Here, the same kind of situation is happening. We are treating these accelerations and taking them to the other side, treating them as some forces. So that's why often you hear the term gyroscopic force. And the last thing I want to do here before maybe writing an example to make things more concrete is that if we treat these effects as forces, so write this G to be, take these terms to the other side to be minus of Gij q dot j, j from 1 to n. So if we treat this as a force, we can calculate the power of G, the rate of work it's doing. And again, remember, power is this is Gi. Power is force times the velocity. So the total power of this is its effect on all coordinates. So power of G is sum of I from 1 to n. This G times Gi q dot I. And I can substitute its definition, I from 1 to n. Sum of Gij q dot j, and j is from 1 to n, q dot I. Uh-oh, my laptop has started doing this again. And so notice that because these Gij's are always come in opposite pairs, Gij equals minus Gji, and because of the symmetry we have, this total summation will always end up canceling, and what we get is 0. In other words, these gyroscopic quote-unquote forces do not interact with the energy of the system. They do not do positive or negative work, and they're just completely passive, or only kind of changes the shape or form of the energy of the system. All right, so that is that. But I think this video can use an example to see what we're doing. So let's do an example. Let's have our inertia frame, xy. This is inertia. And a smaller frame. Oops, that's not good. The xy frame, it's rotating at a rate of omega. So this angle is omega t. And I have a particle happily moving in this two-dimensional space. I'm going to take my two generalized coordinates, q1 and q2, to be the coordinates in these rotating frames, local frame. And I might have some forces, Fx and Fy, acting on the system. So let's derive the equations of motion, see some of these effects showing up. So before I do that, let me bring your attention to this. We are somehow prescribing the motion, some motion in the system outside of the dynamics of the system itself. So this is where we expect the gyroscopic effects to show up. So that's something to note. So everything, let's pretend, is in a horizontal two-dimensional space. So potential energy is 0. And from here, my Lagrangian is actually only the kinetic energy of the system. To do that, kinetic energy, let me write it here, is 1/2 mv squared. We need to find the velocity in terms of these generalized coordinates q1 and q2. Let me write them as, let me do this, q1 equals x, q2 equals y, because it's going to be easier to work with x and y rather than q1 and q2 in this example. So I know velocity in the inertial frame is velocity, the relative velocity that the observer that moves with the rotating frame sees, plus the rotational effect of the frame itself, omega, cross the position of the point in that space. So this v is x dot I plus y dot j, and my omega is omega k in the positive k direction cross xi plus y j. And if I carry out this cross product, what I get is x, is it minus omega y I, x dot, plus y dot plus omega x j. And from here, v squared is the square root of that. So write it down. So t, or Lagrangian, let's speak like this, Lagrangian is 1/2 m this squared plus that squared. So x dot squared plus y dot squared. Those are those terms. I have a minus 2x dot omega y plus 2 y dot omega x plus omega squared times y x squared plus y squared. Okay, to find the equations of motion, what I do, you are a master of this by now, d over dt of partial L partial q dot I minus partial L partial qi equals my generalized forces qi in that direction, or maybe it's called it q prime. So I have two generalized coordinates. So for or along x, q1 equals x along that direction. I have mx double dot. I'm going to just simplify it, minus 2m omega y dot minus m omega squared x equals my generalized force along x is actually the force along x, so that's that. And equations along the second coordinates, which is y. So I have m y double dot minus 2m, or this one is plus. This one is plus 2m omega x dot minus m omega squared y equals f y. So now these two are my gyroscopic effects that show up, and you can notice you can keep backtrack it, see where it came from. They came from the external effect is omega, it was rotating, and the possible movement in the two directions. So it is the Coriolis forces, if you think of it. And also one other thing. So along in the equation along x, so in the first equation, I have minus 2m omega y dot. Let me write it down. No, that's EQ along x. I have this term minus 2m omega y dot, and equation along y, and minus or plus 2m omega x dot. So one thing to note here is that if my speed is, or velocity, I have some velocity along y, I have these quote unquote gyroscopic forces in the x direction. So it shows up in the x equations, and vice versa in the equations in the y direction. The terms that are dependent on the velocity in the x direction show up. So this is that kind of orthogonality that I was talking about. And the other thing, note the coefficient of these two are equal, have the same form but opposite signs. So that is my G12 equals minus G21. What else? What else did I want to mention here? Yeah, I think that is all. And one last thing. So this 2 omega y dot, so 2 times angular velocity times actual velocity. This is a familiar term that you had seen before. It is actually the Coriolis acceleration. And these gyroscopic forces are the inertial forces that are associated with those gyroscopic accelerations. So let me write it down. Here, gyro forces on quotation marks are inertia forces in the D'Alembert sense. Inertia forces associated with Coriolis acceleration. And in general, all these gyroscopic forces or moments, when we see them in an actual gyroscope, these are the effects of all Coriolis accelerations within the rigid body that come into effect and produce that effect of that is perceived as a moment, as a moment acting on the system. So okay, that is now all I have for now. I said now twice. In the next video, I'll have to just show a very quick description what we really meant by those kind of positive and kind of orthogonal. We'll see it in more detail, and that should be it for this module. All right, I'll see you then.